Hi everyone, welcome back. And now we're moving on to question 15 in the 2019 B test. This question is actually one of my favorite problems because it's super simple to think about. The question reads, a mass of M equals 100 grams is attached to the end of a string right here, so I'll call this of length R is equal to 2 meters, okay? A person swings the mass overhead such that their hand traverses a circle of radius r equals 3 centimeters at angular velocity omega is equal to 10 radians per second ahead of the mass m by an angle of pi over 2. Estimate the force of air resistance on the object. So actually, how the book does it, I don't really agree with. So I'm just gonna do it my way, which gives you the same answer still. So let's first think about what this question is really talking about. It's asking us to find the force of air resistance on the object, given this strange scenario of the ball traveling behind uh, the rotation. So let's first think about what would happen if there was no air resistance, right? If there was no air resistance, that means that it would be traveling in a circle of radius r at this exact center right here, and then the ball. So then, like, if the point was connected right here, that means the ball should have been right here, right? Instead of being pi over 4 behind, it should have been exactly in line, okay? So since the ball's right here, then that means that the string should have connected to a point right over there that isn't at a weird angle. That isn't tangent. But because there's a force of air resistance, it's at this strange angle. And notice that the angle doesn't change over time. It's at static, or it's at equilibrium. The forces are balanced, right? So let's draw out the force diagram on this guy right here. So obviously, there's a force of tension pulling it this way, right? And that this tension force is the centripetal force as well, although we'll be a bit more careful with this later. I'll show you why. But also we have to consider the fact that there's air resistance, so we'll call this small f the force of air resistance, pushing it backwards. So we're assuming that it rotates in this direction. And this force of air resistance actually must be balanced with some force pulling it this way. Otherwise, it always have an angle that's increasing, right? If this force wasn't balanced. And what balances this force? If we think about it, there's no other forces except for these two. And here's where the interesting thing is. The actual force that balances out this small force is this component of the force of tension, right? Because remember that the force of tension is at this angle such that it's tangent to this circle in the middle, right? And because of that, it's not directly parallel. It's not directly tangent to the outer rim of the circle. And if we're considering the circular motion like this of the ball, that means that the center of the circle must be this center. So that means that this is actually the centripetal component of the force. So this is great. So now if we figure out whatever this component of the tension is, that means that this is also the exact same force of air resistance, right? Because these two forces have to be balanced. So now the question comes, how do we find this angle, right? If we find this angle theta, then that means that we take sine of theta times t. And that gives us what the force of air resistance should be. And how we do that is actually through some more geometry. So actually, let's draw it a lot more magnified. So this is actually the small circle, not the big circle. So this has a radius of 3 centimeters or 0.03 meters. And it's connected to the outer rim by this length of rope, which is of 2 meters long, right? And it's only asking us to estimate the force of air resistance on the object, so we can make actually a couple of estimations in this corresponding diagram. So let's start off by drawing another tangent line right here, and then drawing this central line down to the radius. And you notice that this central line is actually the same theta that we want to find in right here, right? So now what exactly is this theta? Well, we know that if we could try to do something with this diagram as of now, but you could try it on your own time. But what I found is actually you can create a little approximation by using the law of cosines. You could draw the line across the diameter of the circle, so it's not actually exactly along the diameter of the circle, but it's very approximately close, and it's only asking us to estimate it, and these answer choices are pretty far apart. We can say that the diameter of this circle approximately is the diameter of the circle is 0.06, not approximately 0.06, but we can say that it's approximately straight through these two tangent points caused by this angle theta, or actually this angle 2 theta, right? And now we can use the law of cosines, right? Because we know that this is 2 meters, we know that this is 2 meters, we know that this is 0.06. So in order to find this angle theta, then we will just use law of cosines. So that's 0.06. Actually, I'm gonna write the log cosine squared. So that's c squared is equal to a squared plus b squared minus 2ab cosine of c, right? This is c, this is a, this is b, and this is angle c. So we plug that in, that's 0.06 squared is equal to 2 squared plus 2 squared minus 2 times 2 times 2, that's 8 cosine of, I'm just going to call this theta, and now divide it by 2 in the end. Okay, and then once you solve this guy out, let's see, 0.06 squared minus 4 minus 4, okay, and then divided by -8, okay, and then the inverse cosine of that. So what I got is that theta is equal to, okay, I'm in degrees, oh, I'll be in degrees, 1.72 about. Okay, and so that means that, I'll call this theta n just for clarification. So that means that theta is just half of that angle, right? What we calculated was just 2 theta, right? So that means that theta is equal to this thing divided by 2, which is equal to 0.86 approximately degrees. Okay, so that means that tension times sine of 0.86 is equal to this force of air resistance. And what is this tension right here? Well, we know that it has a angular velocity of 10 radians per second, right? So that means that if we set tension is equal to, well, we have to first do tension times cosine of 0.86, because that's actually the centripetal component, right? And that's equal to the mass times omega squared times r, right? This is just doing centripetal force calculations. So then we see that tension is equal to, what is this? M omega squared times r. M is 100 grams, so 0.1 kilograms times omega squared. So omega is 10 squared times the radius, which is going to be approximately 2 meters. We can just approximate it like that. So it's about 220, and divided by cosine of 0.6. Okay, so the tension, so right here, if you solve for the tension by plugging in all these values, you get approximately 20. It's a very close approximation. And then if we finally plug this back into here, that means that if you take the sine of this, you get that the answer is 0.3 units. So the answer is D.